Welcome to Bowology 101. This will be the first in a series of videos on bows and their measurable characteristics, in particular with respect to Asiatic bows. All graphs will be taken from my website, asiaticbow.info. Check it out for more details. In today's video, we'll be covering draw force curves and stacking curves. This lecture will consist of a theoretical explanation of each one, along with a practical application. Later on, I will make an extra video going more in depth into the technical aspects of these curves. Let's begin with some simple definitions. I'll add them into the description to make referencing them easier. Broad length is the distance that a bow is drawn from the belly of a bow to wherever the hook is or finger or whatever. This measurement is in inches. Imperial. See technical notes 1 and 2. Poundage is the draw force of the bow measured in pounds at a given draw length. Stacking, state of being. When a bow's draw force curve increases by more than 5.5% per inch, taken from Ronald's video. I've chosen this 5.5% to make discussion easier, and you may or may not experience stacking at this point. Stack, verb. When a bow's draw force curve changes by a large amount. This can be either increasing or decreasing by a large amount. Let's go over a draw force curve. A draw force curve is the curve generated by measuring the poundage of a bow up to a given draw length. You can create a draw force curve that goes up to any draw length. Your bow may break if you try to measure very long draw lengths, but for the purposes of this video and for the data on asiaticbow.info, draw force curves will be measured between the brace height, or as close as we can get it to the brace height, and the stated max draw length of the bow. In our case, we measure this poundage from the belly side of the bow, and we measure this at 1 inch intervals. Then, once we have all these points, we do a bunch of math to smooth it out, giving us this nice draw force curve. The draw force curves can be split up into roughly 3 regions. The preload region, the linear region, and finally, the stacking region. In the preload region, the seals have mechanical advantage, giving you a lot of energy per inch. In the linear region, the draw force curve is mostly linear, which gives you a linear amount of energy per inch. In the stacking region, the draw force curve starts to increase exponentially, and you start to not really get much energy per inch. So what does this actually tell us? Well, the area underneath the draw force curve tells us the total energy stored in the bow. This lets us directly compare the total energy stored by 2 different bows. For example, if we look at these 2 bows and we look at their draw force curves between this point and this point, because that's where their draw force curves have the same, can exist together. We look at the area underneath the light blue curve. We have all of this area. And then we can see that for the dark blue curve, we have all the red area plus a little more. That shows us that the blue bow, at the blue draw force curve, has more total energy within this area. I'm going to put this out here because I know that I'm going to get people trying to say this. But more energy stored does not make a bow better. It just means that the bow is able to store more energy. This does not tell us anything about how efficiently it uses that energy, i.e. how efficiently it transfers the energy into an arrow, nor does it tell us anything about how the bow itself will behave. For example, hand shock. The stacking curve is the derivative of the draw force curve. On this plot, it is this purple curve right here. What this means is that it is a measurement of how fast the draw force curve is changing. It measures how many pounds a bow increases or decreases per inch drawn between 2 points. Note that the shape of this curve is similar to a quadratic for both bows. During the preload region of the bow's draw force curve, the bow has a lot of negative stack. The required force to pull it back per inch is rapidly decreasing due to using up the preload from the bow's geometry. When we get into the linear region, the bow's stacking curve remains fairly constant. The value doesn't change by much, as it is in the linear region. Let's go over an example. If we look at this curve at about 10 inches, this is about 5 lbpi. If we look at about just past 20 inches, this looks like a lowest point. That's just over 1, we'll call it 1.3 lbpi. That means that between these 2 points, there was negative 3.7 pounds per inch. What does this curve actually tell us? The curve lets us know how a bow actually feels to draw. The higher the value of the stacking curve at a given draw length, the harder that it will feel to pull the bow as you're moving more pounds per inch. In this example, the LBPI is pretty linear, which most people would perceive as being a smooth bow or a bow that doesn't stack. We convert this value into a percentage of the peak poundage of the bow instead of an absolute value. We can get a percentage value of how much the draw force increases at that point. Most people seem to perceive stacking at around 5.5% increase in draw weight per inch. Also going to point out now that whether or not a bow stacks at a given draw length or not is not necessarily a bad thing. All that it means is that the bow's draw weight is going to start to change rapidly at that draw length. Some people prefer stacking their bows at or near their draw length due to it acting as a wall to pull against, letting them know when to release. Some people like linear bows,